Hello and welcome to Solved, where we help you solve problems. In this video, we will be discussing the material balance of crystallizers. I will be teaching you some tips on how to convert solubility data to mass fraction data, which is very important for crystallizers. Here's the problem. The solubility of barium nitrate at 100 degrees Celsius is 34 grams per 100 grams of water, and at 0 degrees Celsius is 5 grams per 100 grams of water. If you start with 100 grams of barium nitrate and make a saturated solution in water at 100 degrees Celsius, how much water is required? If the saturated solution is cooled to 0 degrees Celsius, how much barium nitrate is precipitated out of the solution? The precipitated crystals carry with them on their surface 4 grams of water per 100 grams of crystals. Let's go ahead and solve this problem. Here we have our diagram for the problem. For a crystallizer, the default is you have 3 process streams. The only input stream is the feed, which is a saturated solution at a high temperature, and then the outputs are a crystal product, labeled here as C, and a mother liquor labeled as ML. The mother liquor and the crystal are at a lower temperature because for you to be able to crystallize a salt out of a solution, you need to often decrease the temperature of the solution so that the solubility will also decrease, leading to supersaturation and crystallization. The two output streams here, C and ML, represent two different parts of your product. The crystal product C is the solid part of your product, that is your precipitated crystal, while your mother liquor is the liquid part of your product, that is the leftover saturated solution. So one thing to always keep in mind is that the feed is often a saturated solution at a high temperature, while the mother liquor is always a saturated solution at a lower temperature. The difference in temperature between the feed and the mother liquor is what crystallizes your salt. Our salt in this case is barium nitrate. We are also given the solubility data for barium nitrate, and solubility data is often expressed in terms of this unit. At 0 degrees Celsius, the solubility is 5 grams of salt, barium nitrate, per 100 grams of water. If you take a look at the denominator, it is expressed only in terms of water. Our interpretation of this solubility is, at 0 degrees Celsius, if you have 100 grams of water, you can only dissolve 5 grams of barium nitrate in that amount of water. If you want to dissolve more amounts of the barium nitrate, then you have to increase the amount of water. If you contrast that data with the solubility at 100 degrees Celsius, you would see that we have a higher value. We have 34 grams of salt per 100 grams of water. For every 100 grams of water, you are able to dissolve 34 grams of barium nitrate in order to reach saturation. The compositions of the streams are often decided using the solubility data. We can get the mass fraction of barium nitrate and water just by using these values. We will get to that later. Let's first answer the first question. How much water is needed to make a saturated solution at 100 degrees Celsius? We were asked to start at 100 grams of barium nitrate, so that would be our basis for the first part of the problem. At 100 degrees Celsius, the solubility is 34 grams of barium nitrate per 100 grams of water. We are just going to use a unit factor method to determine how much water do we need to use. Starting with the 100 grams of the salt, we multiply the solubility such that in the denominator we have 34 grams of salt, and the corresponding amount of water to that is 100 grams of water. Essentially, we are using the solubility data as a conversion factor between the amount of salt to be dissolved and the amount of water that will dissolve that amount of salt. If you take a look at the cancellation of units, grams of salt would cancel, and we can directly determine the amount of water needed. That is 100 times 100 divided by 34. The answer is 294.12 grams of water. This is the amount of water required to dissolve 100 grams of barium nitrates to form a saturated solution at 100 degrees Celsius. If you lower the temperature, you would require more water to dissolve the 100 grams of barium nitrate because the solubility goes down. Now, let us relate this to our crystallization problem. The second part of the problem asks us, for 100 grams of barium nitrate dissolved in 294.12 grams of water, how much barium nitrate is precipitated? we are pertaining to the amount of barium nitrate that will be recovered through the crystal product. Remember that in a crystallizer, we are lowering the temperature of a saturated solution to precipitate the salt. So now let's figure out how much of the 100 grams of barium nitrate originally present in the feed would come out as a crystal product. Before we do that, we have to figure out what are the compositions of the streams. We need the compositions in terms of mass fractions so that we can factor that out into our material balances. For the compositions of the feed and the mother liquor streams, you always take a look at the solubility data. Since the feed is at 100 degrees Celsius, this is your hot saturated solution, the corresponding solubility that we will use is the 34 grams of barium nitrate per 100 grams of water. To figure out the mass fraction of barium nitrate in the feed, we will be setting a mini basis. We are going to say that in the feed stream, we are going to set a temporary basis, and that is 100 grams of water. You can figure out why I chose a basis of 100 grams of water. That is the denominator of our solubility data. That means that if you have 100 grams of water, it follows that you also have 34 grams of barium nitrate or the salt. And now, what we have effectively done is we have determined the amounts of barium nitrate and water in our feed stream for our temporary basis. This allows us to determine the mass fraction of the salt in the feed stream. That would simply be the mass of the salt in the numerator, 34 grams, divided by the total mass of the solution, that is 34 grams of salt plus 100 grams of water. That will be calculated as 34 over 134. The mass fraction of barium nitrate in the feed is 0.2537. It also follows that the mass fraction of water in the feed stream is simply 1 minus 0.2537. That is 0.7463. This approach is always what we're going to do to convert solubility data to mass fraction of the components. And you can use this for the feed and for the mother liquor as long as they are saturated solutions. You can verify the validity of what we have done here by setting a mini basis. If you take a look at your feed, we were able to figure out the amounts of salt, barium nitrate, and water that are in a saturated solution at 100 degrees Celsius. That means that whatever mass fraction we get for barium nitrate using this set of data should be equal to the mass fraction that we determined earlier. Let's perform a quick calculation. That would be in the numerator, 100 grams of barium nitrate. In the denominator, that's 100 plus the amount of water, 294.12 grams. And the result is 0.2537. That's the same as the one we obtained using our mini basis. This tells us that this mini basis works regardless of the amount of the feed or of the mother liquor. Okay, so for crystallization problems, you can use this technique to figure out the composition of the streams. Let's continue this analysis and figure out the composition of the mother liquor. In the mother liquor, you can also assume a basis of 100 grams of H2O. This is a temporary basis, and you will not be using this kind of basis outside of determining the mass fraction of barium nitrate in the mother liquor. So for the mother liquor, we determine the mass fraction of the salt as 5 grams of salt divided by 5 grams of salt plus 100 grams of salt. That is essentially 5 divided by 105, and we calculate that as 0.0476. That's the mass fraction of barium nitrate in the mother liquor. And of course, you subtract this from 1, you get the mass fraction of water. That is 0.9524. For the next part of our solution, we are going to apply the same treatment to our crystal product. If you take a look at our crystal product stream, it was specified that for every 100 grams of crystal product, there is an adhering 4 grams of water. It's important to understand that the crystal product is actually mixed with the mother liquor upon crystallization. That is, the crystals are forming in the supersaturated solution. We are only representing the crystals separate with the mother liquor in this case because we are assuming because we are assuming that the filtration of the solids, which is the crystal, is included in the crystallization. Essentially, what that means is we have a built-in filter inside of the crystallizer that separates the solid products from the liquid product. And as such, since it is only filtered, then we can assume that there is some water left adhering into our crystal product. And in this problem, that is 4 grams of water per 100 grams of the crystal product. In this instance, we can simply assume that our denominator, 100 grams of C, pertains to the wet crystal product, that is C. So when you say you have 4 grams of water per 100 grams of the crystal product or the wet crystal product, that essentially means that we have 4% water and 96% salt. This is already their percentage by mass. There are some problems wherein this composition is not given in this analysis. You might be given 4 grams of mother liquor solution per 100 grams of crystal product. That's a different analysis. Or you might be given 4 grams of water per 100 grams of dry crystal product. That's also a different analysis. But for now, let us stick with this analysis. Let me first clear some of these other calculations and then we'll proceed with the material balances. For the rest of the problem, we will be sticking with our initial basis, which was 100 grams of barium nitrate or the salt in our feed stream. Let's proceed with our overall material balance or OMB, that is F is equal to C plus ML. We know the mass of the feed stream. This was calculated on the previous part of the problem, that is 394.12 is equal to C plus ML. This is our equation number 1. For our second equation, let's proceed to a component balance. The component balance in the case of crystallizers would be the balance of the salt. Our salt balance is 100. This is the amount of barium nitrate in the feed is equal to 0.96 times C plus 0.0476 times ml. We'll call this equation 2. 0.96 is the mass fraction of the salt in the crystal product, while 0.0476 is the mass fraction of the salt in the mother liquor. This highlights the importance of determining the compositions of the streams prior to the material balance. As you notice, we have equations 1 and 2 containing two unknowns, that's C and ML. With that, we have to solve these two equations simultaneously. You can proceed with either elimination or substitution, but I will show you how to do this in the calculator. This is mode 5.1 for a two-equation, two-unknown system. Our coefficients are 1, 1, and 394.12. For the second equation, the coefficients are 0.96, 0.0476, and 100. Essentially, I am treating C as our X and ML as our Y. Our crystal product C is 89.04 grams, while our mother liquor product is 305.08 grams. These are the masses of our output streams, crystal and mother liquor. But to answer the problem, we have to continue the calculations because we are asked how much barium nitrate is precipitated. We have to keep in mind that our crystal product is not pure barium nitrate. It's only 96% pure. So to determine how much barium nitrate was precipitated, we simply multiply 89.04 with 96%. And that is 85.48 grams. This is the amount of barium nitrate that was precipitated. Of course, since we started with 100 grams of barium nitrate, we can also express this in terms of a percent. This is 85.48% is precipitated. In terms of the efficiency of the process, we can say that this is an efficient crystallization because majority of the barium nitrate was precipitated or recovered out of the solution. The remaining barium nitrate, that is around 15% that was not precipitated, is in the mother liquor solution. And that is how we solve a material balance problem involving a crystallizer. That's it for this video. Thank you for being here and I'll see you on the next one.